Okay, when we look at the CPU versus GPU, you see that you have some sort of control and then caching mechanisms and some ALU, which is a smaller part of the let's say CPU. Only about 20% of the transistors will be for ALU. On the other hand, for a GPU, you see that control is a smaller part, and the pipeline part of the GPU actually is all about ALUs. So you have, therefore, more things to do in a smaller amount of time. So you have more power, but not necessarily, let's say, more flexible to do everything. Now let's look at actually this rasterization based rendering. So what we have is we have a 3D screen, a scene, and then we have a rendering process, and then we put everything into a screen buffer. So this is the simple inner working of, well, let's say, the hardware for doing this thing, right? So the scene is going to have your points, lines, and simple objects, as well as your triangles. This will be the facets that you will be using to represent your geometry outside of the geometry, boundary of the geometry. And then there will be rendering primitives for these, and we are going to discuss how to do that. So there are several parts, actually 2 parts of the thing. One part is a transformation. And this transformation is actually takes the transform of the coordinate frames from object to your world, and then world to your camera. So it brings the 3D scene in front of the virtual camera. And then it also decides, the transform also decides the visible triangles and shows them on screen, right? The lighting simulates the lighting transport in the general case, and the idea is to compute the final color of each pixel on the screen, not necessarily just the triangles, but each pixel on the scene, depending on optical characteristic of its material and also the lighting environment. This will actually have several things: surface, material itself, the texture if there is any, and the lighting, of course. So if we assume that our scene is actually made up of just 3D triangles like this, you have a triangle in your world coordinate system. Now what you want to do is you want to actually render this one. Of course, this can work for points or segments if you want to. So the idea here is the pipeline that we are talking about is this way. So you take your world triangle, you do a modeling transformation. So this is a modeling transformation that takes your world to next to your camera, right? So this is your camera. So this it actually does the geometry transformation of your world to be aligned with your virtual camera. So this is the modeling view, or the modeling matrix, or modeling transformation. And then you have a view matrix or view transformation, where this actually is, this takes the view coordinates to the eye coordinates. So this is actually now taking to the kind of the eye coordinates. And then this is the now the entire thing here is actually now in viewing coordinate system. And then you have the projection matrix. If you recall, this 3x4 matrix that takes your 3D world to a 2D world. And now this is not sufficient. You have to do some sort of clipping. This is the viewport matrix. You have to do the clipping and so forth. And then because not everything is going to be visible in your view, some of the things are going to be invisible. Perhaps let's say your portions of your triangle is going to be visible, but not other portion. Then you'll do actually the clipping. And then you have once you have the clipping achieved through viewport matrix, then you have the scene space, screen space. Now, you can see that in terms of let's say processing, this is a pipeline. So while you are actually, let's say, doing your clipping and viewport, you can start actually doing let's say for your next frame, you can start doing model transform, or you can try your viewed matrix transform, or your projection, or your viewpoint, and so forth. So you have, at least in this case, 1, 2, 3, 4 things that you can do at the same time. Of course, one of them is going to be for the current frame. The other one is going to be for the next frame and the next frame and the next frame and so forth. So you can actually use this pipeline to speed things up. And the way that actually this is done on a hardware is something like this. You have the vertices, points in 3D. You have the computations per vertex. These involve TM, this model transform, viewing transform, and projection. And then once you have the projected vertices in 2D, you have this viewing transform. This is the setup. And then after this, you have the rasterizer. This is also very, very important and very expensive part of the thing. And here we have a lot of, let's say, possibilities to parallelize things. All right. So here you have the fragments, you have the potential pixels, and then you have the computations per fragments, and you have the final pixels in your screen buffer. Right. So 3D vertices, the transform is actually gonna take them to your 2D view, and then rasterizer is gonna actually raster them something like this. All right. And then once you have the fragments, you are going to actually process these fragments to finalize as your pixels. So the lighting is going to be done during the transform phase of the thing here. And then you can also add that in the fragment processing as well. So you can have 2 places where you can actually include your lighting transformation. All right. So when you look at the workload itself, this part is per vertex. This is the geometry. And this part is now per fragment. Close to per pixel is not necessarily exactly per pixel. This is the rastering subsystem, and it actually works per fragment, like these entries here. So there are this rasterization-based rendering. There are some bottlenecks, of course. One is in the geometric subsystem. Application is actually transform limited. You have to transform things, and geometry also. In the bus, you can be having these things in the bus, meaning data transfer, bandwidth limitation, and then also the CPU. You can have also a limitation on the CPU, on the processing that you can do. All right. Past these are not that important, but so let's see how, let's say, this is expanded to triangles. As we said, this is easy. we have the same thing here. We have this processing, the geometry processing per vertex, and then once you set up actually the rasterization is going to be actually simple. We're going to talk about that in a few minutes again, but when you have, let's say, just a point or a line, let's say, line will be easy. Again, you'll have the geometry transformation that you'll be mapping this to a line, to vertices here, and then there is gonna be rasterization of this thing, and the rasterization is gonna actually take this thing and rasterize this way, and then it will be, of course, rasterized at the final subpixel, final screen buffer. Similarly, for a point, you'll have its corresponding vertex after the transformation, per vertex transformation, and then you have some area of that in the image, and then you'll actually render that, and then you'll finalize it in your final pixels or screen buffer. So you see this part remains the same. Rasterization changes a little bit for point, for let's say line, and for triangle. It changes a little bit. So you have a point rasterizer, you have a triangle rasterizer, and you have a segment rasterizer. All right, segment meaning a line segment. So each vertex is transformed, projected from 3D space to 2D space, and this can be done independently from all other vertices. So this can be done in parallel. There is no problem here, and independently of the primitive it belongs to. So you don't need to actually worry about rasterization here at this level. So it is all about vertices. Vertices as a vertex for a point, or two vertices for a line. And so this is single, and three vertices for a triangle. So what you can do is you can now assume that you have your cores here. Let's say you have each of these 1000 cores, core 1 to core 1000. And what this is gonna do is you have, they are now actually gonna take the same transformation, let's say some transformation matrix, taking your vertex coordinate x1, y1, z1, 1, and multiplying this and returning, perhaps if this is a 3x4 matrix, returning a UV coordinate. That's it. So what you do here is, once you actually get this transformation thing in place, you can actually use your, let's say each of your core to do one vertex. So this is embarrassingly parallel, meaning you can now have, let's say, if you have 2000 cores, and you can do, let's say, if this is working on 1 gigahertz, let's say, then you can actually process this times 2000 vertices at the same time. So this is 1 to the 9, 10 to the 9, and you have 10 to the 3 times 2. This is the number of vertices that you can actually, in principle, process. So this is quite a lot. This is very nice, and this can be done in parallel very fast. Once you have the primitive, so either a line segment or a vertex or a triangle, then you have the rasterization. And rasterization is also interestingly simple. So the way that you can look at the rasterization, we are going to get a little bit more on that in a few minutes. But if you are rasterizing a line, let's say like this, what you are doing is you are actually building, let's say, you can, in principle, find the values of pixels that are going to actually be lighted by this thing easily. And the primitive can be triangle segments or points, and there is a distinct rasterizer for each of these, and they can be done independently of the other primitives. So you can rasterize a triangle, a segment, a point, and multiple of them at the same time without one. So this is one rasterization, perhaps this is the other rasterization that you are doing, and another rasterization is this one. So they don't need to be actually considered together. You can actually do them separately. So each of these rasterization will actually give you a fragment of the thing. So this is one fragment of the image, and this is another fragment, and this is another fragment. And now you are going to actually put each fragment in position. So independently from the other fragments again, independently from the primitive that has generated it, output of the computation is a pixel in the pixel screen buffer at position X and Y. All right, so this is very, very simple as well. And the way that actually now it works is this way. Let's see here, you can include property of a material and normal here. You can do the transformation here, apply lighting. You include the per vertex coloring, perhaps, as part of the lighting, and you can interpret color using the rasterizers, and then you can actually get the final color as part of your interpolated fragments, and they are interpolated together to put up the final image. Okay, so this the final color can actually also implement things like, let's say, shading, some shading algorithms like Garo shading, for example. You see the Garo shading here. This is the color, and you see this one actually is looking, let's say, without the interpolation, looking somehow geometry is actually showing up here, and then you can actually smooth this using Garo shading. Similarly, you can smooth these things here using this, and then similarly here you can actually smooth this thing with Garo shading. And Phong shading is another idea that actually works here. You interpolate normal in the face and renormalize, and you apply lighting. So this is part of, again, this entire thing. So the way that actually now shading actually happens is you include the properties of the material and the normal here, and then you transform both normal and the position as part of this thing. Now, instead of only pixel locations, you have the normal transformation, and then you have now the transformed normals. You interpolate those normals as part of your rasterizer, and then you use the interpolated normals here, and you renormalize and apply lighting to obtain your fragment color. So again, these shading operators, again, the shading operator is something like this. So if you have a surface like this, these are two surfaces like this, surface patches, what happens is that you say, okay, you have a normal here, perhaps you have a normal here, and you have a surface normal here, and so forth, or maybe a surface normal for this guy and surface normal for this guy. But if you actually use these two surface normals as it is, then you'll see a sharp change from here to here. And these shading models from Goro, what they do is actually they simulate a smooth transition between these two. And you can see that is part of the rasterizer as well as the geometry here. So you can actually put these into simply into the pipeline. You find the vertices, you find the normals as part of your transformations, and then during the rasterization, you actually you know how to go from here to here as part of your rasterization, and add your shading model to this one. You say, okay, I will actually add the lighting here, and the intensity is going to actually increase a little bit as I go from here to here, and perhaps when I go from here to here, it will decrease a little bit. Right? So this could be part of the rasterizer, and again, the pipeline doesn't change. The specifics of the implementation doesn't change. They actually you can use per vertex lighting like Goro shading or per fragment lighting like Phong shading. You can actually use these both in the in this thing. So this is flat shading with just each surface having its own form of or own normal, and Goro shading actually doing this per vertex lighting. And Phong shading, you can see that actually it's much smoother because these interactions between these things are handled better with the Phong shading. So let's look at actually the rasterization process a little bit closer. So I'm doing a point. So this is a point. This is where it's supposed to be. The question is, how am I going to actually rasterize this, right? So a point in principle is actually an infinitesimally small thing, but I want to actually show it somehow. And in that case, I need to actually decide the size, first of all, right? And the shape of that thing. Is it a, let's say, it's going to be 1 pixel length, 2 pixel length? It's going to be, let's say, oval, like maybe I want to put my point like this, and it's going to actually have a flat color or flat shading, or it's going to actually start stronger here and go slower to, let's say, towards the boundary. It will go, let's say, lighter and lighter, right? So first of all, I need to decide which pixels to light. This is the first one. You can actually do just round the point and get the coordinates. So you can round it, and then when you round it, perhaps you are gonna get this one. Okay, and or maybe you are gonna get actually this corner here, and then now you know that you are actually lighting either 4 of these corners or pixels, or maybe a little bit less or whatever. You have to decide on this one. So this is probably the simplest one. And if you are actually doing something else, for example, you might say, okay, if you have some shading, then you can say, okay, now I look at actually some sort of an interpolation. I look at this guy and I say, okay, this one, if I want to actually light these 4 pixels, I can light this one the more because the most, because this is closer to here. This is it's close enough, and this is far, and this is a little bit closer than the others, right? So this might be the highest intensity. This might be maybe a little bit less intensity, and this might be again a little bit even less, and this might be even lesser, right? Something like this. But of course, these type of things will require calculations. So if I want to actually, let's say, if I just want to do the rounding, I will only do actually if some if statement, right? Or not even an if. I will take my number, floating point number, and just get rid of the floating part of it. All right. So the decimal part of it. Now, this is very, very fast. If I want to actually get this distance and light it accordingly, I need to do some sort of, let's say, x0 square plus y minus y0 square and a square root perhaps. Maybe I don't need a square root, I can go for the square, but this is, let's say, just one flap of operation per vertex. Now this is 1, 2, and at least 3 flaps of operation. So this is 3 times, at least for one of them 3 times, and you have 4 pixels, then you'll have 12 flaps of operation versus just 1 flap operation. So this is quite expensive, 12 times more expensive than this one. So you have to think about if this is worth it or not. Lines, similarly. So how am I gonna actually render this line? I have the pixel coordinate here, I have the pixel coordinate here. So what we can do is the simplest thing that we can do is we can do actually integer coordinates. We say, okay, I'm gonna work with integer coordinates only. Rounding occurs before computation, and we only take care of the endpoints. All right. So we actually do it this way. You can see now that from starting from here, I actually rounded it. And now I will actually go for either this guy or I have, after this one, I have several possibilities. I have this possibility, this one, and this one, this one, and this one, and this one, and this one. I have 9 possibilities. Out of this 9, there is only one of them actually gonna work, right? And this is defined by the line's let's say aim or slope. So the slope of the line is going to define that this is going to be this one. And for the next one, similarly, I have multiple options, and the only options that is closer to me is this one. For the next one, similarly, I have again 9 options. I'm gonna go back. This is my only option, and so forth. So there are very fast algorithms for doing this one. One is due to Brazenham. This is one of the algorithms. We want to actually have a sequence of fragments best approximated the line, and it should be as straight as possible. And then what we can do is we can look at the slope, and assuming that the slope is actually less than 1, then in that case we can actually assume that this is 1 fragment per column. So what you do is you see here, depending on this number, considering line thickness and so forth, you can actually easily do this one with a simple algorithm. Similarly, when the slope is larger than this, you can actually go for another one. So you have 2 options here. You have slope larger than 1 and slopes smaller than 1 and equal to 1. And you have these 2 algorithms or these 2 approaches very simply defining you the line. So what you do here, for example, you take your M. M is you take your analytic form of your line if this is this one, and you know that it is less than A is less than 1. You take this part, you know the dx, you know dy. Okay, the number of pixels in X direction to move and 1 number of pixels in Y direction to move. And then when you actually do this division, you know that this is 7 to 9. Okay, now what you do is you restrive from x0, 0 and x0, y0 to x1, y1. So this is the first point. And then your second point, what you do is you compute A and B such that this is for this, you round y, you produce a fragment xy, and you increment x. So this is 1, you do this, and then you do this, and so forth. And then you actually choose you just do the integer arithmetic. So this is a very, very simple algorithm. If you want to have a tick line, you can do the same thing. You can actually now when you actually take this position, you actually in the vertical, you add 2 more pixels to it. And when you actually get this one, you may add 2 more pixels. When you get this one, you get 2 more pixels and so forth. So adding a thickness is gonna be just once you have X and Y, you just say, okay, you have X and Y, you have X, Y plus 1, and you have X, and you have this one, you have this one, and you have X and Y minus 1. So these are all integer arithmetic. It's very, very simple, and you can actually achieve a thickness of anything that you want. Now, of course, this is gonna have some problems, what we call aliasing problem. Aliasing problem is actually is an error due to passing from continuous to digital representation, right? Okay. And an anti-aliasing algorithm is going to be needed. For example, this is an aliasing problem. So since I go actually from continuous to digital, I have lighted these pixels. You can see, and it's supposed to be actually this one. Now, this thing looks like very digital. It doesn't look very nice. So I need to have an anti-aliasing algorithm. So the way that we can do this is actually say, okay, if I actually light this part, this part, this part, this part, this part, this part with a similar color, but with a let's say less intensity, then I should perhaps see this as a straight line. This is the anti-aliasing algorithm. And the rasterizers actually have those, this line rasterizers will have those type of abilities to actually add. All right. Of course, you can see that this aliasing is going to be expensive, more expensive than actually just non-aliased ones. But still, you can have very efficient algorithms to actually put these in place. It will get some extra cost, but the cost may not be as big. So here, when you say, okay, I want to have lines with anti-aliasing, let's say, then you may, let's say, depending on how many lines you have, you might have, let's say, some performance drop. So it may be 5%, maybe 10%, it may be even less than that. But depending on, again, the type of aliasing that you are going to use. So the realism will cost you, of course, additional computational power, and therefore, if you have, let's say, already not enough computational power to actually do this thing in real time, then you'll actually see the effects of that in your system. So let's look at the triangles. The idea is going to be very, very simple with the triangles as well. So when you have actually a triangle like this, you sort your thing by Y, and now you have essentially, when you get to this guy, you know where this triangle actually starts here. This is your pixel, and now this becomes a line segment, and then you actually render this line segment for each row from y min to y max. So this is y min to y max. You actually first find the fragment A inside the span. So this is fragment, and then find first fragment B outside the span. So this is inside, outside, inside. Produce fragments along scan line from A to B. Is how you actually would render this. All right. So this is just to make just this algorithm a little bit faster, because now you can actually process them two at a time, or say some blocks at a time, 2 by 2 blocks or something like that, to actually make the parallelism faster here. Otherwise, you cannot actually parallelize this one, at least for a single triangle. So there are other tests that you have to do, like, let's say, things like you'll need a point in triangle test. Given a, let's say, triangle, do you have that point, a given point, is it actually in the triangle itself? And the way that you actually do this one is very simple. You have your vertices, you have these vertices here, and then you actually look at the half planes. There are half planes that are actually formed by your vertices. This is the first one, this is the second one, this is the first one. So let's say this is the first one, V0, let's say V1 and V2. And this is the first half plane, this is second half plane, and this is third half plane. And when you have actually this line here, you can decide if a point is on the right hand side of that half plane or not. So this is just a ax plus by plus c equals 0. And depending on x position, when you plug it in here, depending on actually if this is less than 0, it's going to be inside. It's larger than 0, it's going to be outside. So when you do this test for each of these half planes, you say, okay, after 3 half planes, if they are both saying that it is inside, then you know that it is inside. So this way, what you do is now each of these ax plus by plus c, the positive or negative thing here, you can actually do this one in parallel. So for each line, you can actually run these things for each of these. So this is a simple arithmetic, right? So each core actually takes one of these half planes, and then you can actually test them all, and then you can decide which one actually gives all yeses. If you get all yeses, you know that fragment is inside the front-facing triangle or otherwise. All right. So these are techniques to actually make these tests very efficient. Now, one of the tests that we will need to do is the clipping. So the clipping is going to be, we know that the primitives that we are going to be displaying, they are going to be only portions of them will be displayed, because I have a field of view. So if I have a triangle like this here, another triangle here, another triangle here, let's say like this, and my field of view is only actually covering this part, let's say. This is my field of view. What will happen is that I need to actually clip this triangle off, perhaps this triangle off, and this triangle off. So there has to be some clipping so that I don't need to process these. I know that they are going to be unnecessary. So this is one of the processing that we are going to be doing often. So the question that we are going to ask is a primitive that is totally inside of the volume. If they are totally inside, we are going to actually say that they are there. We are going to actually get them. So if a triangle is inside our volume, and we say this is a volume because our camera geometry is actually defined by, let's say, something like this, right? So if this is our camera geometry, our camera geometry is defined by a volume of composed of this frustum. So this is the camera center, this is the image plane that I want to actually achieve, and the pyramidal shape, some let's say infinite pyramid here, that is actually available to me. This part of the pyramid, so this is called a frustum. This frustum is going to be the only part that I can actually see things. So anything outside this frustum is going to be invisible to me. So if I have a primitive here and a primitive here, this is not going to be visible. So anything inside is going to be visible. Okay, this is fine. This is called, they are retained. Anything that is fully outside, like this one, this is going to be removed. It's called cold. And then anything actually is in the boundary, which this part is going to be visible, but this part is going to be removed, is called clipped. So we are going to be first clipping things, and we don't need to do anything with the cold objects, the cold ones, and we don't need, we'll do something with these guys, of course, And the important part is actually how do we clip these things so that we know only the necessary part available to us. Okay. So in the past, people were actually doing the clipping before the viewpoint transformation, right? So this will actually minimize the rasterized area. But since actually we are doing the rasterization much faster with the GPUs, clipping can be actually done alongside with the rasterization. Now, instead of actually doing the clipping on the, let's say, on the volume here, we can actually go back and do this in the rasterization. If this is the rasterized triangle, and if this is my actual image area, I can actually start now saying, okay, for this fragment here, I know that this fragment is already outside my viewing area, so I can drop it. This fragment I can drop, and then this fragment I can actually render, and this fragment I can render, this fragment I can render. So this is now actually is part of the rasterization, and you can do this in parallel, of course. And you have the kind of the advantage here. So if you do this before the viewpoint, so meaning that, let's say, if this triangle in my viewpoint is half, let's say, is blocked like this, so this part is not seen, and this part needs to be clipped. So now, how do I clip this one? So this is a difficult decision to do. So, right, what I need to do is I need to find this clipping thing here, and I need to now generate a new triangle, perhaps with this one or with this one here. So there are going to be two new triangles generated for this one. Now, when I do generate these two new triangles, I have to take care of also their normals, and I have to take care of also their texture coordinates if there are any, and other things. Now, we are saying, okay, now you don't need to do that. Just do this at the very end or as part of your rasterization process. So this is what I described. So this triangulation of the new is going to be quite expensive to do actually. Instead, what we do is we look at the fragment, and if the fragment is outside the boundary, you just clip it. If it is inside the boundary, you actually just render it. So there is also this bake face calling. So if you have a, let's say an object, let's say if you have this object here in front of you, let's say something like this, right? Now you know that if I'm looking at from this one, I will see this side of the cube and this side of the cube and this side, but there are three other sides that I cannot see from my perspective. So I need to call them as well. So this is done usually very simply, depending on, of course, the closed and opaque object. So if you have to actually worry about opaqueness and also the closeness of the object. So this is a closed object, and assuming that it's an opaque object, then you actually check the surface normal. So you have a surface normal, let's say like this, and then you are here, and if the surface normal is actually making an angle more than, let's say, 100 and let's say 9, let me see, more than 90 degree, right? You know, if this is my angle, yeah, if this is more than 90 degree, if it is more than 90 degree, then you actually remove that. So this is called back face calling. All right. Of course, there are cases where you'll actually have partially occluded surfaces, like for example this one here. This surface is partially occluded and this surface is partially occluded. So you cannot call them because, or if you want to call them, you have to actually create a new surface that is actually visible. So this is probably a good idea to actually do with the rasterization as well. So you can actually check if the patch that you are going to actually generate is going to be called from your perspective. So these are quite expensive things, but they have to be done to generate the proper virtual rendering. Okay, so there are some algorithms. And one of the algorithms that you can actually use is this painter's algorithm, some sort of depth sorting or depth, let's say, again, depth sorting algorithm. And the depth sorting, you can actually, for each pixel, you can decide, you can actually keep also the depth information. And then once you actually have all the pixels actually, let's say, formed with different depths, you can actually just sort them from smaller to the larger, and smaller ones will actually take over. So that will be a way to easily actually sort the depths of your pixels. And in that case, you can actually achieve this simple back surface calling, or back face calling, or invisible surface calling, and so forth. So this is called also depth buffer or Z buffer. So you use per fragment operations comparing the depth of fragments to get to the same location. That gets to the same location. So for each pixel now you have a depth buffer, and depth buffer will actually be updated with this depth of the object that you'll actually render or raster. So what you have now is along with your screen buffer, you have a depth buffer, and this depth buffer is also quite important. This is actually helping your let's say your the renderer to decide which pixel to actually get, but at the same time, this buffer actually is gonna give you, from your perspective, some information about the depth of the visible point. Now, you can use this font for object selection as well, because what you are doing here is that if you have, this is your image. Now, this image is your screen buffer, so pixel buffer. And let's say if there is this pixel here, and you know the depth of this pixel, so you know the depth information is available. Now you have some idea of actually where this pixel is in 3D, like a let's say a point cloud data. You can think of this as a point cloud data now. Now this means that I know actually from my perspective, when I actually look at a pixel, when I choose a pixel with the depth buffer, I know approximate location of that X, Y, Z in world. So this is of course in camera coordinate, and I can do an inverse transform of my world to camera. And then now I have XW, YW, and ZW. So this is my now 3D point in the world, and now I can perhaps see where this is actually hitting my object, which part of the object it is actually hitting or getting from. So this type of this depth buffer can be used for multiple purposes as well. And for your, if you recall in your homework, when you pick a pixel in your image or in your screen, that pixel actually has a depth buffer associated with the thing. And if this depth buffer, let's say you can see it this way, this is my texture video, this is my 3D object, and this is my camera. And when I click a point here, I know the depth of this one. The depth could be either here or could be here. If this is outside the object, I know this distance because this is given to me. So I can say, okay, this is actually hitting, so something like this one is hitting no object, but something like this is hitting my object because this depth is closer to than this one. So this is a very important thing. So this is a simpler way of actually doing, let's say, ray casting. So ray casting would have get this ray here and extend it into the 3D and say, okay, where does this actually cut the object? So for that one, I have to actually do all sorts of triangle ray intersection. So if I have 1 million triangle, I have to actually search for that 1 million triangle to intersect with this guy. Whereas now I have this depth information available to me, and it makes my searching job quite faster, perhaps. So this shows an example where I can actually use the depth buffer with a 6-bit buffer with values from 0 to 63. So what happens is that this depth buffer, because of, or the Z buffer, because of the memory requirements, cannot be very big. So usually it will be, let's say, 8-bit or 6-bit or something like that. So you cannot hold actually, let's say, values here that are, let's say, that is gonna cover a wide range, right? So this means that if your object is here, object depth is here, and you are here, then you are gonna actually, and then your viewpoint is here, you are gonna actually normalize this distance, this entire span to that number of bits. So you can see that this is not going to be exact. There will be a lot of, let's say, discretization here. So the accuracy of this representation is not going to be very big. And if you make a big depth buffer with a, let's say, with a lot of bits, then you can perhaps get a better and better, let's say, resolution. But your memory is going to be actually much and much minimal, and it may not fit into your, let's say, GPU, and therefore GPU will actually limit your Z buffer, let's say, resolution. Of course, you have this something called Z fighting. Z fighting is actually a phenomenon that happens when we have, let's say, a depth buffer that is actually, let's say, very low resolution. So when you have a low res depth buffer, you have two objects here. One is this guy, and then the other one, two patches. One is this one, and one is this one here. And you have these two depth buffers, and you want to actually merge them. Right. What happens is that because of the, let's say, resolution, at this pixel, this thing actually picks up something from the first object. So this is the first object, this is the second object. Here, it picks up from the second object. Here, it picks up from the first object, and so forth, because of the, again, resolution. So you have your actual pixel is here, right? So this is the one, And if your, let's say, if your depth and then the other actual pixel is here, the second one is here, let's say, the second one, the round of error here might actually say, okay, this is this guy. But in the other one, you perhaps have the other, just next pixel is a little bit tilted. Now this is closer. One is actually one is closer to this guy than two. Then it will actually, in this case, it will pick this one. In the other one, it will pick this one. So they will be fighting for the Z buffer here, and you'll see these type of streaking effects, so aliasing effects because of the Z fighting. So this happens quite a bit in places where you have, let's say, two planes very close to each other, right? And the way that actually you can prevent this thing to actually add more, perhaps, let's say, depth resolution here. So if you have more and more depth resolution, this will be actually much better, and this will probably go away. But then if you have more and more of these things, you'll have requirement for your memory, and this is premium, at a premium and expensive. Of course, not just the expense of this one, of course, also you have a lot of other things going on here. So you cannot actually afford a very large depth buffer usually. And you see another sea of fighting here. You see there are two objects, one blue and one gray, and you see a lot of, let's say, depth problems with your object here. So let's summarize what is going on here. So as we said, we have some view and model transformation and some projection transformation, and then viewport matrix. The way that actually each vertex is transformed, projected on from 3D space to 2D space, independent for others, it can be done in parallel, and it is actually independent of the primitive that we actually use. For each primitive, we actually use rasterization, and different primitives, triangles, segments, and points can be done. And there is a distinct rasterizer for each of these primitives. They can be done independent from each other. You can rasterize the corresponding fragments. And once you have the fragments, now they are in XY coordinate, you can independently process them from other fragments. You can independently process them from the primitives that has generated them. The output of the computation is a pixel buffer, but you can also use a depth buffer and so forth in this thing. Okay, we discussed this one, and that's about it for rendering. So if we are talking about, let's say, you see that the rendering with a GPU has, let's say, changed the let's say classical pipeline from, let's say, you convert everything to 2D, you call them, you clip them, and then at the end you restore them, versus you actually even do the let's say depth clipping and visible surface clipping as part of your actual rasterization process, because again, the advantage of what the GPU is actually bringing. Meaning you can do things independently with a lot of cores, with very simple, let's say, arithmetic logic operations, like just simple multiplications and additions, and maybe some comparisons. Okay, so with this one, we now have an understanding of actually how the let's say rendering is happening. Next week, I'm gonna talk a little bit about usability and some user interface design concepts, and we'll move from we'll move to the other topics from that. So, are there any questions?
Can we say that today's lecture was the toughest topic in the scope of this course? Would you say that?
Not the toughest, but probably we went very fast. So I'm actually just giving this. I'm not gonna be, let's say, expecting you to know. Usually, this entire thing that we discussed in the last 2 hours, a little bit more than 2 hours, is usually is covered in an entire semester in a graphics course, right? So this is a very quick, very fast and concise, let's say, summary of what is happening with graphics. I don't need to go into the details of the graphics in this course as much, like for example, shaders, like let's say lighting, like texture mapping, but this basic idea of rasterization, the view transforms and so forth is necessary for you to understand how to actually do the augmentation. And if you want to read a little bit further into this one, you are welcome. You should probably, but you can still, let's say, function as an AR programmer, perhaps, at some level without knowing these topics or these concepts in detail. But my aim here is to give you just a quick, let's say, overview of what is there and what these simple concepts are. And you can read and follow a little bit, follow up a little bit deeper if you want to. So you are right. This is difficult, not because it's more difficult than the other things in theoretically, but we usually need to spend more time to understand these things in full. Again, it's entire semester's topic, but I would say tracking was much more difficult than this one because tracking actually involves computer vision, graphics, geometry, and algebra and stuff. So it is much more difficult than this one. This may seem a little bit difficult, but because of the time that I am actually reserving for this.
I see. Also, sir, may I ask something about the homework, if possible?
Sure.
Yeah, this might seem like a silly question, but knowing the nature of our school, I feel like I need to ask this.
Sure.
In the homework, are we actually expected to implement a function that that finds the homography matrix, or can we use
You
something
can
like?
use an existing one, yeah.
Sorry?
You can use an existing algorithm, but I don't want you to use, let's say, so if you have your, I need to look it up first of all. Let me see. Just I may give you a wrong information. I need to check one thing with the homework. So yes, so the C# function that you need to write for finding the homography, you need to implement one. But so if you recall, the homography algorithm is an optimization algorithm. It's it can be either formed as a linear system, or it can be formed as an optimization problem. And I'm not expecting you to actually have a linear solver implemented by yourself or an optimization algorithm implemented by yourself. So you can use, let's say, linear algebra package, or like LimPack or LayPack or whatever, or some others to actually do those things. But I'm expecting you to not to use, let's say, call a homography calculator from OpenCV, for example.
I see. That was my question, my
Yeah.
intent. Yeah. Okay.
I mean, as you can see here, I would have said, okay, just calculate the homography. I'm not saying that. I'm saying write a C function that given the set of correspondences, calculates the corresponding homography matrix. So this requires you to kind of understand how to set up that system of equations, right? So if you have, let's say, 4 of these things, you'll have overdetermined system, and that will require a LIMPAC, some sort of a optimization algorithm. And the simplest algorithm will be most probably Levenberg-Marquardt algorithm. So you can use that one. But I don't expect you to implement Levenberg-Marquardt or let's say a linear solver or a Gaussian solver or whatever. So those are gonna be
In that
used.
case, could we use Python, for example, instead of this C#, or is it like explicit?
I am expecting C# because again, this will be part of. I mean, don't force that one. I mean, if you can do this in Python, you can do this in C#. That's simple enough. The reason that I want this to be in C# because we are doing everything in Python, not Python, Unity.
Yeah.
Therefore, it should be actually within C#.
I see. Thank you, sir.
Sir, I have also one question, but do you have any time for me?
Regarding
sorry.
As part of the class or later in
the class, yes, it's
okay.
about the topic.
Let me do it this way. Let me stop the recording because I am done with today's lecture. So I'm gonna stop the recording.